So welcome everyone to the lecture number 12. This is a penultimate, I think you call it, lecture, because the number 13 will be the last this semester. And we will do next semester anyway, so why, it's a natural place to cut off anyway, so it will be fine. So on last lecture we introduced some ideology behind the Schrieffer-Wolff transformation. So we had a Hamiltonian with an energy gap, right? And we analyzed what is the consequence of a gap being there, and one of the consequences that if it's very big, you can neglect what's happening above the gap and maybe think of the physics dynamics going on only below the gap. So we have an idea to have an effective lower dimensional theory, let's say, of some system. And then we said, okay, this is fine and good, but what if some perturbation comes in, and this perturbation actually starts to connect energy levels from below and above the gap, right? Can we still maintain, we hope that we can still maintain this idea that we have this low energy, low dimensional effective theory, but now we have to somehow deal with the fact that there are some transitions happening that weren't happening before. So we came to the conclusion that what we basically want to do, we want to kind of diagonalize the perturbed Hamiltonian using this transformation generated by S and the anti-Hermitian operator. This is the Schrieffer-Wolff transformation. And so we wrote down what we want. So this is our founding equation for the problem, which is equivalent to solving an eigenproblem. But this form, where you solve for S and energy levels, this is convenient to a perturbative approach, right? Because our idea was, okay, we probably cannot solve it exactly, so we will try to do a perturbative approach, which is basically, okay, let's assume that this thing we are looking for can be represented by a power series, okay? And let's try to basically solve smaller problems for every order of the perturbation theory. And so we took our founding equation, we substituted this form, this series form of our solutions, and then we expanded everything, the founding equation, into the power series. We had left side and the right side. It's like if this equality is to hold, it has to hold for every order of the parameter independently. So this is how you get the infinite series of equations, which we hope that we can solve them iteratively, going from the lowest order to next order, next order, next order. And when we decide to stop, we will get our approximation of the given order. So we did that, and now is the time to actually make an attempt at solving. Yes?
Just a quick summary. So the condition for that gap was the gap should be larger than the block width or height, right?
Is it a real condition? I said that let's have a big gap. Big in comparison
to you reduce that capital omega and small omega, you wrote the condition. So that condition is effectively telling.
Where is it?
Yeah, I think it's there. Yeah, that image.
There was somewhere.
Yeah, that one. Yeah.
Yeah.
Omega G1 would be the width of the block or height of the block in terms of energy, like lower minus highest, and the gap should be larger than that.
Let's assume this for now, okay? Because we will On the last lecture, we will go into we will make a proper breakdown everything analysis of this Schrieffer-Wolff transformation. We check when it exists, what are the conditions, the convergence radius, and this will give you when on technical level everything exists. But to have this ideological motivation for why to do the effective theories, I think it's good when the gap is actually big in comparison to what, let's say, to the actual blocks where you are working in. Although it won't be key to actually solving our perturbation equations, but for what are we doing here? This is kind of good to have in mind that maybe this is something you should keep, this condition. Okay, so it won't be key for mathematical reasons, but for ideological and physical it might.
And also, I guess you need to have slightly better condition when you have applying this to a middle block, right? Because
no, you can.
You can still work with this.
Look, you have to be inventive.
Okay, yeah, fine. Yeah, I didn't want to jump in, I just wanted to make sure I understood that condition.
This won't be key for the procedure to work, okay? But it's a part of doing physics, right? You have to be. You're not a bureaucrat who's following your procedure, right? You are the one who creates procedures, so you have to, You are the authority. You are the government who sets up the rules, right?
You say that something is right, so it's right.
Yeah, you might try that. Maybe it won't go through without a fight from the others. But you have to have something about it. But this is a big in comparison to what.
I can tell you from my experience that it's not straight. There is no universal criterion that will always work. Sometimes this ratio between omega large and omega small has to go beyond 1/10, so that it's nicely converging the perturbative results and the full dynamics results. And sometimes, once I had something that I could even make them almost equal, and it was still working very nice.
The radius of convergence, we will discuss it in the next lecture, so we have better feeling what are the conditions.
For sure, this one is not a strict condition.
This
one is concept.
This doesn't enter into radius of convergence. Okay, let me just say this. If you estimate it correctly, it won't enter. But Hubert has some and Navid, they both are actually using Schrieffer-Wolff transformation in their work, so they have some hands-on experience in this stuff. Although Schrieffer-Wolff transformation of this idea of effective theories is way more broad than just this stuff we are talking about here, the technical level. I'm still trying to understand this, to have a coherent picture of everything. I will try to share with you today about some thoughts on this matter. But let's start with some honest calculations, something that everyone can agree on some level without thinking too much. Yeah. So we have this set of equations, right? So let's try to solve them see if we can solve them actually, because we came here in let's just do it. We don't have a proper theory yet to explain when this exists, will it be solvable, and so on. Let's just do it, man. Which is when you are actually doing some stuff, you have and you are trying this perturbative approach, there is no sense in the beginning to try and but is this convergent, absolutely convergent series? Don't worry about it at first. Worry about it when you get something sensible, because then, I'm onto something. Now, is it actually real? Then you might think about the convergence and stuff like that. But in the beginning, you just go for it. So we'll just go for it and you know, play it by the ear, by a ear. We just roll with the punches. Oh, that's better.
I may make a very short comment, because in high school they first always tell you in mathematics class, check the domain of the equation before you solve it and stuff like this, and only when you have everything prepared you can start solving it. And then in a real life, as we have now, I hope it's real, we actually do completely other way around. We first try and then we say, oh, I'm getting something, is it real? Is it in the domain? Is it converging?
Because, you know, again, scientist is not a bureaucrat. You are not here to follow a procedure given you from somewhere. You question, I mean, sometimes you of course follow some procedures, but you should question, okay, well, where it came from. And you realize, okay, it just came from other guys like me. One day you are following a procedure, the other way you are giving procedures. Right? So you just
on the humans.
You question stuff, you know, where it comes from. So, you know, if someone tells, oh, you should do it like this and that. Well, I disagree. And I want to do it differently. Whatever works, right? This is like there is always time for trying to formalize everything when there is a need for that. Okay, you have time for this. Sometimes, you know, you just don't do it. Just leave it for the next generation to worry about. Okay. Anyway, let's try to do some stuff. So yeah, let's start with the zero order. Right? Zero order equation is I already written it for our consumption. So this guy was yapping so much that the tablet turned off. So this guy is actually, if we also realize that Hamiltonian, right? It also has spectral decomposition. H-E-E, right? I mean, I don't have to do much to actually solve this equation for zero order energy, right? So from this, zero order is very simple.
Sorry, what was E? I forgot that.
E is like dimension of the whole space.
Okay.
The whole space.
Okay.
So G, when we do index B low, we sum up to G. G is where the gap starts. When A both, we go from G plus 1 to D.
Tutti game timers.
Yeah, so zero order for energy. We have immediate solution that E0 B equals HB. So this makes sense. There is no zero order describes when there is no perturbation. So no perturbation is just Hamiltonian, which we already know what its eigenproblem is. So this is quick and easy. So let's move to first order. First order. When we move to the first order gives us an operator equation. Okay, this is equality for two operators, for left-hand side and right-hand side operators. So it's it's actually many equations at the same time, right? If you think about operator as a matrix, which means that we have some room to maneuver here. Let me find the place in my notes. Oh my God, this is too complicated. Oh, this is the top. So we have a operator equation of the form sum over B low BG E1, so first order correction to energy, B's. So I will just split the split in two over G E1A A equals, and the left hand side is V perturbation and the S1 first order generator commuting with Hamiltonian. Okay, so this is the operator equation. So if it's operator equation, we can like start taking matrix elements. And there are three distinct like categories we can take. We can take a diagonal terms. That would be one distinct thing. We can take an off-diagonal terms, but below the gap, and we can take off-diagonal terms that connect below and above. We don't care what's happening above at the moment. We are focused on doing stuff on, we are looking to find an effective theory in the low energy subspace. So first start diagonal terms. So we sandwich everything. In between the some BB, right? We put everything here on left and the right hand side, which means that left hand side we actually get something out of it. So we will have E1B equals, we will have a diagonal element of the perturbation plus a diagonal element of this commutator here. This commutator here. And now, if you remember, I said that let us assume for simplicity that V is actually, the only thing it does, it connects it's purely off diagonal, let's say, that it connects the higher energy block with low energy block, but it has nothing inside each block. I argued that if there was something I call it W, which like works inside the block, perturbation inside the block, we could drag it along with us here, so it would have some contributions in this particular equation, for example. But I said, okay, let's not worry about it here. Maybe you can always, not always, but sometimes you can think, okay, there's this V, let's just like absorb it to H, and like re-diagonalize everything, and just don't worry about it. So you can always do this whole stuff, this extra term, but it's just messy. Okay, so for this initial approach, let's just forget it. So this guy is purely block of diagonals, so this will be 0.
When you take the diagonals, I mean, there used to be, is it because you're only taking the diagonal parts of the lower energy gap, or do we consider also all of the diagonal?
So you can consider, of course, you can consider the upper block if you want, but we think of the low and effective theory. So you could get another category where you take the AA, right? That would be fine.
Okay.
But you will see that we can skip it at the moment. But sure, sure, you can do it and then see what happens. So this guy, where is my cursor? So this one is 0. This is fine, and this guy here, which is S1 times H minus H times S1, which is nice because these are eigenvectors of H. So we can like just convert them into numbers. So this is very, very convenient, and we get that, if we do that, we get, so a diagonal element of S1, which we are looking for, times HB, so the eigenvalue, minus eigenvalue, the same diagonal element. Right, so this is kind of, so we have a diagonal element, which we are looking for also, but here we have HB minus HB. This is a pattern that happens from time to time with all these calculations. So this is 0. Oh, this is 0. In other words, so already from this, we know that therefore the first order correction to energy is 0, which is okay, it happens. But it also tells us that this equation gives us no information about these diagonal elements of S. As a matter of fact, this is the only place where it comes in. So essentially, these diagonal elements of S1 are free parameters, as far as we know. So let's just assume they are 0. So in other words, let's make it S also a block of diagonal matrix. So let's assume S1 and also, because why not, and also all of Sk to be block of diagonal. So in other words, things like this, or even K, will be 0. Okay? If we are wrong about this, we will find out sooner or later. Okay? If we are wrong, then we will get to some point where we cannot solve the equations, and we will we have to revise the assumption. As it happens, in my foreknowledge, this is actually correct assumption. This S will be always block of diagonal. That's one of the properties. So the first order equation, what it tells us is basically that the energy, the first order correction to energy is 0. This is what we got from this guy. So this guy equals 0. Okay, so that was option 1, diagonal terms. Let's take off diagonal terms. Off diagonal matrix elements. Inside low energy block, subspace block. So we take B prime. We take stuff like this, which gives us first of all, the left hand side doesn't contribute because it's purely block diagonal, which is nice. So we get equation 0 equals B prime, non-zero, because V is okay.
It should be 0, right? Because
it is 0. Yeah, it is 0, because the only thing that V does is connects A and B, not BB. So this is again 0, which is very good. And we get our guy here, the S1, H, the commutator, but this time not diagonal, but off diagonal. We know the tricks, so this gives us B, S1, B prime, and we will have eigenvalues, but this time it's non-zero. So this is not a non-trivial contribution. This is non-zero in general. As a matter of fact, this is actually omega BP prime, according to our fancy definitions. So this is non-zero term. All of it equals 0. Therefore, this guy has to be 0.
All of it has to be equal 0 because we assume that this V is not W, yes?
Yes.
Okay. Right.
Yes. Which is nice because things are simple. what this means that S is of diagonal, but it's actually block of diagonal, right? It's like V. S is like V essentially, which is actually cool. I mean, it's cool. It's a simplification. Yeah, draw variables, the coolest thing ever. It's a thing, it's a result. So final case is we take a matrix element, oh my god, element. That was supposed to be element. Okay, like elemental, remember. So again, the left-hand side is 0 because it's purely diagonal, so we can set it to 0. Right-hand side gives us BVA. Okay, this is non-zero for sure because this is what V does. This is actual given matrix element. This is the perturbation, and we get plus BS1. A, so also the matrix element of S, and we have the eigenvalues of H, B minus HA. So this is actually omega BA, which is greater or equal to the gap, actually. This is the frequency across the gap. But this is finally some equation to solve. Because this is not 0, and this is what we are looking for. So we can convert it to, if I use my notation for matrix elements, BA equals V BA divided by omega, AB, actually. Because I take this, move it to the left-hand side, so I get a minus. I can absorb minus in omega. So BA, AB. Okay?
Shouldn't it be HA minus HB in the first equation?
That's a good point. S, H. Oh, you're right.
But you can just put a minus sign there.
Yeah.
Let's do it correctly. Because you know that this mind, I'm sure that everything is correct up to some minus.
Up to some phase global.
Yeah, to some global phase. Yeah, this is true. True. So now I move it. And so it should be BA, right? That's even nicer, I guess. That's even nicer. Okay. What else? So zero is work for diagonal. All right. So that's if we assume, that it's S will be purely block of diagonal. That's all we need. We actually this is everything about S1. So we actually determined from all these considerations. We determined first order for the generator.
I think I got a bit lost between all of the approximations, so to speak, because we are doing the expansion on the order of lambda. But also, if we are expecting the gap to be big, wouldn't that mean that the BA terms of the generator are also small, right? So would they still have a, so to speak, measurable impact on our expansion because we are also multiplying by lambda?
That is correct. It has impact, of course. on the magnitude of terms, but we are doing expansion, treating lambda as a variable, right? So it's is it big or is it small? We'll kind of find out, and you know, if it's big or it's small in comparison to what. Yeah. So it's like it's kind of natural that some extra parameters that will quantify the magnitude of some things in your system will come into it. I mean, also V has some magnitudes, right? It's like omega has one. So it's like the lambda is small. We'll probably at some point have to figure out how small it has to be to actually for all of this to converge, and it will be probably expressed in some terms of gap, right? And actually it will be some fraction of gap, and so it will come up. So it's actually it's like this denominator here, frequency denominator. It like also suppresses our series, which is probably good. If it was exploding, that would probably work against us. Then we probably have some real trouble with convergence. But this is actually the opposite problem. I mean, not a problem.
So the equation previous to this, we assume that there are no degeneracies like the previous page.
Okay, okay, that's true. If it was there was the degeneration, right? This would be 0, and then we will be back at the previous problem where we would just have to so free parameter. So let's 0 anyway. If it's not degenerated, this is non-zero. So we just know this is 0. So this is how we weasel our way out. Again, more systematic analysis, which we'll do next lecture, will actually reveal that we are not guessing. We are guessing correctly. But this is like imagine we are just in the trenches. We are just seeing the problem first time. We have to start somehow. So we doing what we can. We just run from one trench to the other. There's a machine gun fire. There are artillery, drones are everywhere.
That's a good optic to ask for the 2%.
Yeah, exactly. Dodging and weaving.
Can we talk about V also later?
V?
Yeah, like imagine you have a Hamiltonian that conserves a certain symmetry and certain physics. And then how should this V react so that we go from the one manifold, energy manifold. So we have this dynamics. Because if V just respect everything but it's 0 respects, then there would be no not after.
There will commute with
so there will be no after.
Yeah. It's that's a good. This is a good point, right? That it's like.
Otherwise, we are going to trap in this energy manifold.
Yes. Let's leave this for later, okay? Because it is an interesting topic, and maybe we will come up with some good talk about it. But it's like Hamiltonian can have some symmetries, right? So those energy levels and those speeds, maybe there will be some degeneracy. Some symmetries, and then comes in the perturbation that breaks this symmetry, which in particular would mean that you have some blocks, energy blocks become connected through it. So it's like V explicit because it does not commute with H, because it's not diagonal in the same basis. It explicitly breaks symmetries of Hamiltonian, which is thing to have in mind, I guess. Well, let's see. Well, maybe we can figure out something clever to say later. So let me write down the solution for S as an operator. So here what I written in my notes, and and it's all up to sign, of course. But what I've written here?
To e to the power I pi.
So we would have here a matrix element of V, and I go. So here what I wrote in my notes. I wrote it like this, which is probably wrong at the moment. So it probably should be BA if this observation was correct. So let's stick to our guns. So let's write it like this. And then we will have here the other part, BA. V itself is Hermitian. Okay, so VAB equals VBA star. And omega BA and AB. Okay, so BA, AB. The minus here, is necessary so that the S operator is anti-Hermitian. Remember, we assume it's anti-Hermitian so that it can generate unitary transformations. So we arrived at, it's this solution tells us that it's actually anti-Hermitian, which is correct. Okay. So we have a first order correction. We also have first order correction to energy, which was 0, which sucks. So if the first order is 0, we have to check to find the lowest order that is actually non-zero. So we are forced to look for second order to check second order for energy. And G, which how do you get it? Well, you have to go to lambda square, which I neglected to write for you on the lecture, but it's in the notes. And you can, if you did the assignment, you know what it is. Okay? And take a diagonal part, the diagonal matrix element, so that the left-hand side gives you the energy. So this means we take B second lambda squared stuff B, okay? The diagonal part. And the equation you get looks the following way: E to B, so the energy, and it equals matrix element S1, which we know, which we already got, which is fine because this is the thing. If we obtain, let's say, S3 here on the right hand side, we are in trouble because that would mean we cannot solve this iteratively. But this is here, V. There's also S2 here, commuting with H, S2. And 1/2 of S1, the nested commutator of S1 with S1 on H and B, okay? And you can do the algebra if you want to see. I mean, this guy will give us 0 because we are assuming that S is always block of diagonal. Okay, so this would just 0 out, so we don't have to worry about it. Very good. This guy we have under control, and this you have to do the double commutator. I won't do the algebra in front of you because probably you'll find more minuses somewhere on the way. But according to my calculations, and this what we should get is that we have here A greater than G, absolute value of matrix element BA square over omega, AB. Should be AB or BA? It's BA. And minus 1 time the same thing. So this comes from this, I believe. and the second part comes from this. If I didn't make more mistakes. So, this cancels with this, and we end up with the. So this is the correct form. BA squared divided by omega BA. I think it's correct. Maybe it should be AB actually, up to minus, but let's roll with this. Yeah, so we have a lowest order correction to energy, lowest order correction to S. So we didn't fail along the way, which means that, so I guess our assumptions were kind of correct. We got our, we won. I mean, we should congratulate. we got something. Of course, it was as you saw, it was we are fighting in trenches. There was no procedure right now. We are just trying something out, right? So we will, next lecture, I will show you what people, post hoc devised for this, to make this procedure more formal and to see all the stuff. But this is how you would do it if you were trying to figure out something on your own. So you just don't worry about convergence, minus here, minus there, whatever. You would have to test if this leads to some nonsense along the way and find the error. But this is how it's done.
Do you know any examples where you might think that perturbation theory might help, but you run into the problem that you were saying that the order equation depends on the next order?
I believe. It's. I don't know example of that, but probably this is because
if you have a non-linear differential equation, I think you might end up with that. Because you're substituting back into the differential equation. Because you have linear, I think it's very unlikely.
I don't know, because when I was doing some stuff, I was doing with some expansions of X, and they are blessed, of course, so it's like everything is nice, and it works automatically. But
depends. I think it depends on the non-linearity, right? Yes.
I mean, I don't know an example actually, but I suspect that it's like maybe it's rare that it's rare when it's fine. Maybe it's I don't know actually. Is it rare that it's fine or it's rare that it's not fine? I don't know. But there are some. I guess there are some techniques to force it. I mean, on next lecture maybe we'll see some, because they are doing some specific stuff, which I think it's like forcing the issue. But it's I don't know. Maybe someday we will find something. Maybe you will find something, and then you can tell me, so I can have a cautionary tale. But we are lucky here. So we got it. So probably we were yapping here. We were yapping, but it wasn't so bad. So let's take a break for now, a couple of minutes, and then we will talk about the philosophy of all of this. Okay, so let's try to carry on. So we have some formulas. We had some formulas, and so now I wanted to talk about. I entitled this section 3.4, and I call it applications of Schrieffer-Wolff SW theorem. And don't worry, we won't be discussing concrete examples. That's not what we do here. We live in an abstract. So we started all this story with the gap thinking of, maybe we can compact our theory to this low energy subspace, to this smaller system essentially. But if we for a second just forget about all these gaps and effective systems and so on and so forth, just look at this Schrieffer-Wolff transformation just on the face of it, what it does, right? And of course, what it does, we already said it. It executes a diagonalization, right? So if you forget all about these gaps, what we were doing here actually, we were diagonalizing perturbatively certain operator, right? This perturb Hamiltonian. So this means that one mode of let's say. There is a first mode, is a diagonalization mode. Diagonalization mode of SW theory. So we basically derived some perturbative way to approximately diagonalize a perturbed Hamiltonian. Okay, even if we forget about gaps. But if we want to come back to the story with gaps, it's if you think about it, when gap is big or small, right? It might happen if your perturbation is weak enough. Every level might be, from the point of view of this strength of this perturbation, there might be a gap between every level, right? So if you imagine that you have omega e prime, so energy difference between any one of the any two levels of your unperturbed Hamiltonian divided by 2, and this is much bigger than lambda v. Then from the point of view of this whole theory, we have like single level blocks that are gapped. So we can like do the, so we just execute our Schrieffer-Wolff transformation for every energy level separately, which is nothing else than just diagonalization of our perturbed Hamiltonian. So the thing about this stuff is if you are doing this diagonalization mode, this is what you are doing. So sometimes in textbooks they would just call it a time-independent perturbation theory. Maybe you saw it in textbooks. So this is nothing else but a Schrieffer-Wolff transformation in diagonalization mode. Okay, they just call it a time-independent perturbation theory in like textbooks or whatever. But the consequence of it is
why they call it time-independent?
Because it's distinct. When the Hamiltonian is time-dependent, you have a distinct mode of doing it.
Okay. I thought that just searching for energy corrections is then by contraction time-dependent, and searching for something else like this off-diagonal terms is time-dependent.
Well, but the real explanation is that if you have your Hamiltonian is time-dependent, we haven't touched upon that this possibility yet. But if your Hamiltonian is time-dependent, non-trivially, that is, it does not commute with itself at different points in time, this means that you cannot diagonalize your Hamiltonian. At every point in time, there's a different basis where it is diagonalized, right? So it's like the idea of diagonalizing your Hamiltonian doesn't work anymore, right? Because it's like
there's no eigenvalue equation for time-dependent Hamiltonian. That's
also not a deal in diagonalizing it, even if you diagonalize it for a specific time.
Yeah, it's just
but that's instantaneous. Yeah,
exactly.
It's useful, but that's not the solution to a Schrodinger equation. That's the problem.
And moreover, the evolution operator, it's not. You cannot compute it with some basis that diagonalizes Hamiltonian at some point in time when it's time dependent. Mainly because the evolution operator, next semester we'll talk about it. because the evolution operator of time-dependent Hamiltonian is no longer just x of this Hamiltonian. It's more complicated beast. Okay, so that's why they call it time-dependent perturbation theory, because it's the completely different approach has to be used when you have a time-dependent Hamiltonians. But anyway, so if you are doing this in this mode, there are some consequences. So, for example, if we come back to some correlation functions, right? So we come back to a certain correlation function, t plus x t1 plus, let's say, and some initial condition. Let me put it like this: b 0 minus. Okay. So when you are doing, which translates into a formula as a trace, there is a operator of observable y in Heisenberg picture. So T2 H plus lambda v. So this is like a situation when the perturbation is active, and you have the minus the I in the perturbed Hamiltonian, the T2, and you have X here. Too much, I need more space. IT1 H plus V lambda X T1, and the initial condition EB. I cannot fit it. Projector onto eigenstate of the Hamiltonian, perturbed Hamiltonian, let's say. Something like this. So if you are doing just diagonalization, then what you want to do, because when we knew this spectral decomposition of Hamiltonian and we treated the unperturbed problem, the correlation function, we just put everywhere the decomposition of identity, and we just calculate everything, got our nice formula with phase factors when the frequencies came up, right? So basically you want to do the same thing here, but now you have your eigenstates, eigenvalues, you have to get them from your perturbative diagonalization. So in other words, you take this exact expression and you start putting in the Schrieffer-Wolff transformations. So let's say we could put S again up to minus S minus S, evolution operator, lambda V, T2, S minus S, Y, and so on. Put everywhere, right? This guy nicely simplifies to X of I E minus S H plus lambda V S, right? Which is the left-hand side of our initial problem, right? So we have our results for this diagonalization perturbatively, but you also have to calculate stuff like minus S Y E S, right? Which is, again, we have S perturbatively to the first order. So this guy we can expand. We expand exponents. So we will get something like Y plus lambda S1 Y, and higher order terms, which let's say we haven't calculated them, so let's just neglect them, and so on and so forth. Okay. So when you're doing the diagonalization mode, you're basically taking your thing you want to calculate, some correlation function, because this is what, everything is some kind of correlation function. And then you apply your transformation, but you have calculated it up to some order, so you just expand it in a series, right? So this guy is actually k1 to infinity lambda ks1 sk, sorry, which you can write as 1, where do I have it, plus lambda s1 plus lambda square s2, which we didn't actually get, so we probably have to skip this. No, we did get it. It was 0. Was it 0? I don't remember. And higher orders. So basically, you just do the standard trick with unitary operators and just expand everything. So that would be the diagonalization or Schrieffer-Wolff transformation, which is the same as simply time-independent perturbation theory, from the textbooks. Okay, but the point is you transform everything. So this is like the simplest thing. The gap is not important. The story of gap is not important. Effective theories don't come up. We're just doing we're just diagonalizing stuff with some approximation. So that would be first the most boring mode. The second mode is way more interesting, and I call it effective theory mode. Effective theory mode. So for this mode, the gap is key, right? Because this is the idea, the thing we started with. We want to have this d-dimensional system, d-dimensional theory. We see there is a gap, so there is a motivation to think about a smaller g-dimensional theory that just dynamics that happens inside the low energy space. So, but the perturbation comes in, it gives us, breaks the symmetry, as Navid pointed out, symmetry of Hamiltonian, unperturbed Hamiltonian. There are some explicit transitions between higher and lower energy levels, but we still want to keep our picture of gap in mind, so we executed our Schrieffer-Wolff transformation. So we block diagonalized everything, okay? And now we want to get rid of the higher energy subspace. So what we want to do, we want to essentially create a new system, create a new model for a new system that is smaller. The description must be such that the system is now smaller than the full system, and that its Hilbert space coincides with this low energy subspace of the bigger system. But the dynamics is governed by an effective Hamiltonian, a model Hamiltonian, such that it actually somehow incorporates in a consistent manner that, in reality there is more than to what we are constructing right now. That there is this high energy subspace, and in principle, in reality the transitions are possible, but we just want to incorporate the effects of them. We want to treat them as a virtual transitions only. Okay? Am I making sense to you?
Yeah.
Am I making sense?
The normal equations you usually make.
Okay, so it doesn't answer.
That's a mystery to solve.
So formally, the execution of this mode, it's like you define effective Hamiltonian, HF. So like formally state our intention. So you take, you Schrieffer-Wolff your perturbed Hamiltonian, which we know it block diagonalizes it. And you, to say that I'm really cutting off the high energy subspace, you signify it by sandwiching everything into with projection operators onto the lower dimensional subspace. Okay, so you are saying that, yeah, I just ignore what happens everywhere else. However, there is the Schrieffer-Wolff transformation. Once we execute it, the energies are, we know they are shifted by virtual transitions, because what we get here, up to the order we calculated, this will just turn into B lesser than G. We will have HB, the unperturbed energy level, plus lambda square sum A over G is bigger than G. V matrix element B A square omega B A plus, higher level, higher order terms and BB. Okay, but so we are saying we are shrinking we are inventing new system. We are postulating new system that G-dimensional instead of D-dimensional. Its relation to the full system is that the dynamics of this new, smaller, effective system are derived as a Schrieffer-Wolff transformation of this bigger system. And now what it forces us to do is that, okay, so we are invented this new effective system. So now we also have to invent new observables for the systems, new initial conditions that would make sense for this G-dimensional system, but might not necessarily make sense for D-dimensional system, from which we got here. Okay, so.
But you just mean to rewrite the observables in this new language, in this subspace?
This is
how new is the new that you want to get?
Exactly. So let me write some. So we are inventing new observables. So we will be correlation functions. Let's say y tilde. Why not? X tilde. New. They are completely new. And well, we can initialize in level B, because our eigenstates here are the same as original, so we can just project onto them. And this guy would be so this would be EIT2 H effective. So this is G by G matrix, and our new observable. B prime, B piece. We have some matrix elements, which we would have to define what they are, what they mean. But it's an operator that lives only in this our new, smaller Hilbert space. Okay? And I minus 2, H effective, and similar analogous stuff for X. B prime, B bis, okay. X, oh, you know the drill.
So you just basically project it to that smaller space.
Now.
You only keep that.
Now, to answer this question. In general, there is no need. You are working in this mode, you are inventing new observables, there is no reason to relate them to observables in the bigger system. In other words, there is no need to say that this, let's say, y tilde hat is an effective description of original y, of the y we had here. Okay? So this doesn't have to be, it doesn't have to be y effective, which you would define as a Schrieffer-Wolff transformation of the big Y, which you then project. Okay?
But why is that? How then the orders will be? Because this Y for the bigger space, it can take you out of your subspace. So how are you avoiding that?
If you, instead of inventing Y tilde as something new, you would consider it as an effective description of this bigger Y, and that would be the only observables you are considering, then you would be just reverting back to diagonalization problem. Okay? If you are really taking seriously creating effective theory, you are now in smaller space, g-dimensional space, with new Hamiltonian, this effective Hamiltonian. So it makes sense to have new set of observables. You know, let's say you have, you are starting from some system that has, I don't know, spin 17 or something like that. It's like 2 times 17 plus 1 dimensional system, right? But you are creating an effective theory that is just 2-dimensional, right? So you are in 2-dimensional space, so it makes sense to have spin 1/2 observable, spin 1/2 observable for the system. But the spin 1/2, which would represent with some sigma operators, it's not effective description of spin operators in this spin 17 system.
So, okay.
If you treated it like that, so your new observables are effective observables from the bigger system, you are just going back to the diagonalization mode. Okay?
It's a bit tricky because you see we start with basically the Schrieffer-Wolff is a unitary transformation and we are just keeping up to a certain order, and then that means you have to also transform your operators accordingly, right? And then keep the respective orders.
No, that's
so how are you respecting that order tracking?
No, you don't. That's what I'm saying. If you want to, what you are describing, you transform your operators, you keep track the order, you're doing diagonalization mode there. Okay? I'm saying you're doing something else here. You have some procedure to define new system. Your system is defined by its Hamiltonian, this dynamical law. You are creating new Hamiltonian, effective Hamiltonian.
Yeah.
Which is, and you say it will operate in the smaller
subspace,
smaller dimensional Hilbert
space. Yes.
It coincides with the subspace of the original.
Yes.
But in principle, it's just a completely new system, right?
Yeah. But my problem is the Y. It is defined on the total Hilbert space. Now my doubt is. Now we are talking about the effective Hilbert space, which is a subspace, but the Y can actually take you out of your subspace. So how are you preventing that?
No, I'm saying if you are doing the diagonalization mode, you are dealing with you take your Y that's observable in the big system, the total system, and then you just do this kind of transformation on it, and it can pop you out of the, it can do the transitions everywhere, okay, in whole Hilbert space, to all the dimensions. But that's the diagonalization mode. Here, you say you come in, here is a new system, g-dimensional system, and I have new observables. I just invented them. They are not necessarily effective descriptions of the original observables. Because if you did that, if every observable considering is an effective original observable, then you are just doing diagonalization again.
Yeah, that part I didn't quite catch. Why do you say that it's going to go back to the diagonalization problem?
Yeah, because look, you take this,
Yeah.
you apply it as to the order. That's this formula.
Yeah.
Yeah. So you're just calculating this then.
But we can compute it up to first order. We don't need y to be diagonal. Because now we're talking about making y diagonal. I don't want y diagonal. I want to capture, transform y up to a certain order.
But then you are not doing effective theorem.
Okay, so now it's okay. Now we are okay because you are defining effective theory to be of this form. Okay, yeah.
This is separate.
This is what you mean by effective theory. That's
Exactly.
Okay, yeah.
You are creating a new thing.
Okay, yeah.
For my effective model.
And then this new thing,
Smaller.
you're bothering me. I cannot hear myself think. So you are doing a new thing. We are creating new problem. That's, in a sense, is an approximation of the bigger thing. Okay. So observables don't follow us here. If we dragged the bigger observables, we are just doing diagonalization. Navid, yeah.
Can we just call effective theory the diagonalization in a specific energy subspace?
Diagonalization of Hamiltonian. But,
In a specific energy.
but doing a theory is more than just Hamiltonian, right? For example, you want to consider some dynamical properties. So it's not just I agree. If the only thing you thought about is the Hamiltonians, nothing else matters. Just look at the eigenvalues of Hamiltonian, eigenvectors. Then this distinction wouldn't make any sense between the diagonalization mode and effective theory mode.
No, the previous observables we had, but we use the eigenstates for the distress subspace of the Hamiltonian. Like for example, spin, but not for all eigenstates, for just the specific eigenstates of this energy manifold of the Hamiltonian.
Okay. So you are doing okay. So this is very very good point because there is a one more I want to talk about, but I can already make the comment here. So the thing to consider here is like I'm like pointing those modes, right? But it's like you can mix and match stuff here. Okay? There are no like borders. It's like one mode with the other. You cannot do anything else.
So effective theory could be diagonalization.
I mean, the thing you are describing is like you're doing the diagonalization. What you're saying, okay? If I might put some words into your mouth, you're saying, okay, let me do the diagonalization mode. So I have this, I'm doing the up to the order, all the transformations, they're collecting things. Everything's connected with everything. But then you come in, but there is a gap anyway. So all the transitions across the gap, we have these tags. So let me just neglect them.
Yeah, cutoff. There is a cutoff.
Yeah. So you're doing diagonalization on top of neglecting high frequency corrections due to energy gap, essentially, because Schrieffer-Wolff transformation, our perturbation, preserves gap. We can still presume it's big, right? So it will bring another small correction, right? The transition across the gap. So what you are describing is like you're doing diagonalization plus neglecting across the gap transitions. So it's
and that's effective because we're just projecting the.
Kinda, but not really. You see that. You see this. I mean, this is very subtle because and it's subtle, but it also doesn't really matter, right? Because you are doing some stuff. You can mix and match this stuff, but have it in back of your head that there is this Schrieffer-Wolff transformation can be used as a something to create completely new system with completely new observables. Not only as a diagonalization and neglecting higher order terms. Okay? Is it a effective? I would say if you are not doing this, like there's a new set of observables comes in,
You are not allowed to call it effective.
I wouldn't call it effective theorem. Okay? You're just doing perturbation theory. That's you're just having a complete system and doing perturbation theory. Of course, you don't have to follow this procedure, right? I'm just saying stuff here. You can, I want to show you the differences because there is a third mode. I would like to say because there is a third mode, which the names for those modes. You probably can imagine. I invented this right now, right? So it's like I cannot point it to reference. But how did I call it?
Renormalization mode?
Yeah, exactly. Theory renormalization. Yeah, I almost forgot. Theory renormalization. So creating effective theory was like you have a big theory, you know this big theory, and you do the specific Schrieffer-Wolff transformation to create an effective Hamiltonian, on top of which you build a new system, right? But imagine this kind of scenario. You are just looking at some problem. I don't know, for example, you have a piece of metal, you cool it down, and it starts to, the resistance goes away. Then, how to describe this? How to describe that it's all of a sudden become a superconductor? What's going on here? And you're looking at it, looking at some phenomenology, and you're starting to figure out that based on my intuition and my knowledge about this kind of systems, metals, electrons, conducting electrons, stuff like that, you imagine that if there was a model where there was some effective attraction between electrons rather than repulsion, then that would really explain a lot. I could show a lot of stuff where I had this effective attraction instead of repulsion. And you could okay, the pairs will start to form, the Fermi string will destabilize, all this stuff. And now you have a problem, okay? This is very convenient for me to have this attraction, but why? Why it's here? Where it came from? I mean, it's convenient for me, but I have to justify it somehow. How the actual physical laws, dynamical laws of this system of electrons and nuclei and stuff like that, how can it lead to this kind of thing? And now, because you know about Schrieffer-Wolff transformation and this effective theory mode, you might say, what if I can figure out, so I have this my attraction, it is a kind of effective theory. Right? I just invented the attraction. I mean, I put the attraction so that I have my effects, right? But what if it actually is an effective theory that came from some kind of Schrieffer-Wolff transformation of something bigger? So essentially, you are trying to reverse the Schrieffer-Wolff, the effective theory mode.
It's inverse engineering.
But is there a full theory that?
Well, so you are thinking about, okay, I know, I see how Schrieffer-Wolff works. Can I figure out what can be this perturbation that, the stuff like that. So you're looking at a little bit more experimental data. Oh, there is a isotope effect, so that the mass of the masses of nuclei have some impact on some critical temperature and stuff. So if that is the case, so maybe the phonons are the thing that has to be. The bigger theory actually has electrons and phonons because the vibrations of that would explain the isotopic effect. So you're poking around. It's so let me have a bigger theory with the phonons. There are the electrons, and now let me do get rid of the there's a coupling between electrons and phonons. So let me go back to the just electrons. So let me do a kind of Schrieffer-Wolff transformation, getting rid of the phonons, and oh, here's my attraction. Very nice. So I figure it out. Okay, so this is like, so you have renormalized your electron theory.
It's called renormalized. It's called.
Now, a couple of things. One, this is not really how it happened. Okay, Schrieffer with Cooper and Bardeen PCS did the same Schrieffer from Schrieffer transformation. You know, they figured this pairings and phonons and their stuff. Yeah. This is all true, but it's not. I'm kind of, you know.
Peter Jackson making.
Yeah, I'm making a story here, right? But it is. But what is true is that, you know, you are the problem that you have in real physics, a condensed matter theory and stuff like that. You are often forced to make effective models, but effective in the sense that you are just looking at stuff. If you wanted to start from first principles, you would get nowhere. So we are like trying to isolate what is important in the given problem. So we are postulating models. Let's say, attracting electrons instead of repulsing electrons. Stuff like that. And then it's really your job as a theoretician is then to justify where they come from. Where those models you're postulating coming from.
Can I add something?
Yeah.
Sometimes you have a system and there is a free parameter. And this free parameter makes different regimes. Like the system in a specific subspace of this parameter difference in some way, in some other specific subway difference in other way. So we need these effective Hamiltonians to describe these different subspace of this parameter. Not only just like for this, like the reason you just said. You need it because these different regimes of these different parameters give you different physics.
Exactly. Different effective physics, different effective. Yes, this is where I'm getting. That's why I call it renormalization. Okay, because so this idea that you have a big theory that describes a lot of stuff, and you are like reducing it via some kind of transformation, like Schrieffer-Wolff maybe, or more generally a renormalization, group transformation. You know, there is some, you take big stuff, high energy stuff, the parameter you're talking about could be like a scale of mass, scale of energy, and stuff like that. And you are like reducing something to smaller, effective theory, right, is a very powerful idea. And Schrieffer-Wolff, in this effective theory mode, it's like one of the realization of this idea, right? So if you are aware that this is possible, you know, you are like different. You take your big theory and like specialize it to effective theory in certain regimes of energies, dimensions, whatever, symmetries. I don't know. There are many different things you can try to do. Schrieffer-Wolff is one of the realization of this, but this overall knowledge that this is possible gives you this, leads to this third mode, renormalization mode, that, you know, you look at something and it might come from something more complicated, higher dimensional. And like final conclusion from that would be, you know, we are doing, I mean, already it should be kind of obvious that even on the level of Schrieffer-Wolff transformation, right? This effective Hamiltonian we devised, we derived from the Schrieffer-Wolff transformation up to some order, has some certain form, right? There are some eigenvalues, there is some dimension and so on. But you can probably easily see that the same effective Hamiltonian could be obtained from different full problems, right?
Yes.
Right? There is some terms come in, some matrix elements, but if numerically they are the same as some different matrix elements, you will get the same effective theory. So this is like a process where you reduce stuff. You are just smearing over some information. You are casting out some kind of information about what's happening in the full theory, high energy theory, d-dimensional theory, right? So this is the kind of this reduction, and also that many different incarnations of high-level theory can lead to exactly same low-dimensional, low-energy effective theory, right? That's the consequence. That's why they call it it's not a renormalization group, but a semi-group. It goes one way, cannot go back, because we're losing some information, right? And thus, it means that the idea of emergence comes in. So what happens in this effective theory that we just obtained, it's not directly connected to everything that happens in the high energy full theory. Because some of this was lost, the idea that from different specific high energy theories you get to the same effective theory means that a lot of stuff that happens in this other scale is completely irrelevant. And stuff that happens then in this effective scale, it just doesn't follow logically straight from the dynamical laws in the bigger system. So you have this emergence of new phenomena, new behaviors, new physics.
But there is a point there.
Yeah.
Schrieffer-Wolff only happens when you are in low energies, because it's have this perturbation type of thing.
Well, we discussed that it's the gap is presumably
for
important.
like big energies. What else?
I don't understand. What's the difference? Low energy.
Like, for example, you have this h plus lambda h. We call this like you can use Schrieffer-Wolff because you can use this diagonalization kind of thing that is like a perturbation, as we discussed last session.
Mm-hmm.
What if like the addition to the h0 could not solve? Like you cannot just consider the first or second order terms. You have to go on, and then these are adds more effects.
This means that you simply introduce division in the wrong way.
And then you cannot
you wrongly identified what is the.
No, this I just want to say that this effective theory just based on Schrieffer-Wolff cannot always.
I mean, Schrieffer-Wolff, we think of it as a perturbation theory. So if it doesn't converge, it doesn't work. Yeah. It's the transformation not always exists. That's also true, and it's connected to how big the gap is.
So
if you are required to, if you're creating your effective theory, and you want, include higher order corrections, which you can calculate eventually if you need them,
so it's not systematic. You have to have another thing aside from Schrieffer-Wolff.
Yeah, I mean,
Schrieffer-Wolff is for a specific energy level.
Yeah,
it's clear cut if you are doing this diagonalization. But you don't create anything new. You are just you're just doing calculation with more and more precision. Then it's like there is nothing to think about here. But if you are in this mode of creating effective theories, then the precision has to be, the precision of approximation has to be treated with a little bit more subtlety, because what you want to create is like something that works with some accuracy in this, let's say, low energy subspace. If this translates into including more effective virtual transitions of higher order, then so it be.
I understand.
You understand. But it's not forbidden if you say, you know what, I will just create a effective theory that's it's just up to the second order, and maybe it won't describe my system accurately, but it in principle describes some other system. So there is a subtlety here. Okay.
So just maybe this is what I was asking earlier. Like when we say effective Hamiltonian, we have to specify how we get that. And in this context, we are using Schrieffer-Wolff
Yes.
as the means to get that effective. Now, you earlier mentioned that there are other methods. There might be other methods which might help you to get effective Hamiltonians. So that can be in principle different.
Yes.
Yeah.
Yes.
So then you have to be careful. Like you have to be clear on what you how you get
Effective
that.
Hamiltonian by
But exactly. Yeah. We are talking in that context now.
In other words, we're talking about something that's it's not. There is no one procedure. If you want to be a bureaucrat, there is no one procedure that would work for every case. This is like a real intellectual challenge, how to use this power of effective theories. This idea that you have one theory that can be transformed into other theory, it's huge. It's really, this is like what defines solid state physics for 50 years. This renormalization, it's many branches of physics are defined by this huge idea of emergence of effective theories, connections between theories. People try to formalize it. Renormalization group theory comes in. It gives really big answers to big questions, but it's very subtle. This is highly taxing intellectually. Okay, there is no one procedure that can cover all of this. I just want to because I'm yapping about it to no end, because the first time I was introduced to Schrieffer-Wolff transformation, my immediate reaction was that how is it different from just perturbation?
Yeah, exactly.
The thing I had in my textbook, just the diagonalization. Why are you insisting effective theories? You are just saying stuff, doesn't make any sense. And I was surveying different people with different experiences, and it's like I couldn't get one straight answer. I mean, depending on who you ask, because what they did in past. For example, whether to execute this transformation or use this kind of form, it's like people cannot agree with each other. They don't know. There is no one straight answer. So I realized that the story behind Schrieffer-Wolff transformation, it's way more subtle than one specialist can even see. For some people, it's just diagonalization because this is all they see. For other people, this is their tool for dealing with their system, and they just think of it as I just apply some formulas and I get this HF and I do some stuff with it. For other people, it's solving superconductivity, and it's there is some untapped richness of this where one lifetime of experience cannot capture. So I'm trying to yap about it, that this simple mathematics that we just did, this very simple formula, it is simple formula good because it was complicated, it was even another layer of pain. But the way how you use it can be vary so much between cases that it's just your imagination is the limit, what you can do with it. And this idea that it's the simple maths can allow you to create new systems, postulate new systems by this effective theory mode, or reverse it through renormalization mode. For me, it's mind-bending a bit, but it's also a lot of power. That this is a new way of thinking about how to think about borders between theories. Actually, this shows that there are no borders. This, as Philip Anderson says, you have to think about physics, actually all of the science, as a seamless web. And this is a very nice way of putting seamless because there are no borders, no hard borders, because even a theory of something can move smoothly, maybe smoothly, continuously to add to theory of something else through kind of effective theory mode. Right? So it's like everything should be connected to each other and cannot forget about this. And the fact that this kind of simple Schrieffer-Wolff transformation, mathematically not sophisticated at all, it's like executes this.
I think
It's amazing.
I think this is just a matter of language to some extent, but it's important here because from scratch when you do Schrieffer-Wolff, you work on Hamiltonians, not on eigenvectors, not on energies. They are there, but I always think about them that they are hidden in it. Yeah, I have to let's say pick the energy and then I can say, oh, I just use the energy from the Schrieffer-Wolff. But it's very general, and that's why you can utilize it the way you like. Yeah? Because if you do it on operators, say Hamiltonians, then it's everything. Yeah.
So
what the
actually let me reveal to you something. The back end of the structure of this whole lecture. This particular thing, this modes of Schrieffer-Wolff transformation, was one of the chief motivators behind me doing 7 lectures on this introduction, where you constructed the story to show you that correlation functions is the thing. It's not just states, not just Hamiltonian. It's just they all come together to describe real effects. Because if you forget about it, you go through the standard Schrödinger equation route, you kind of think that physics is Hamiltonian or some state, eigenstate Hamiltonian. And then, when you don't have this context that actually physics is things like this, you cannot appreciate the difference between, let's say, diagonalization mode, where you transform observables, and this effective theory mode, where you invent new observables. Okay? If you don't have this background, it just makes no sense. Because you just say, just new eigenvalues for Hamiltonian. I guess when I will calculate something, I have to I guess I will put energy with a correction. And this is actually a real problem. I talked to my colleague who had some experience and knew some people who had experience, and he told me a story how they debated whether to do this or not do this in the Schrieffer-Wolff approach. Do I have to rotate the observable or not? And they were they couldn't find the answer. And they say, I guess, I don't know. I know energies, I would put the new frequencies, but this, I just have no idea how to approach this.
What about eigenvectors? Should you transform your initial eigenvector, your unperturbed Hamiltonian, and keep order, or you diagonalize your H effective?
Now you're asking about real physical problems, because I put here initialization in one of the eigenstates of the perturbed Hamiltonian, actually.
Mm-hmm.
Right? But why? Maybe correct answer should be I put the P. I should put here instead of this, I should put just B, right?
Yeah.
Maybe. And then, I would have to, if I'm doing the diagonalization mode, I would have to transform it as well.
Sure.
Right?
Sure.
And that would be something completely different than what I did here. But then you ask, what is why I am using as an initialization eigenstates? Where does it come here? What would have to happen when I have a Hamiltonian that's perturbed, and the initialization is actually in the eigenstate of the unperturbed Hamiltonian? What kind of physical
you are time dependent, then you are like switching on or something.
Yeah, because this you could justify by saying, okay, I had some maybe zero temperature thermalization leads me to one of the energy levels of the energy operator. So it would be one of the eigenvalues of the full Hamiltonian. So if instead I put the unperturbed Hamiltonian, well, that would mean there was some intervention from experimentalists. Or maybe actually there was an initialization, but then all of a sudden the perturbation was turned on. But can I describe sudden turning on of perturbation by this formula? This is new physics. But if you have in back of your head that correlation functions is the thing you do, you can parse it out. You have a physical justification. You can find them, right? But if you were just, everything is just eigenstates of Hamiltonian, you would just be at the loss. Yeah.
And how are you preserving the statistics? Because if you are starting with fermionic, I don't see how you can preserve that statistics behavior. Or can you flip it? Start with fermionic.
I'm not surprised you don't see it here, because you shouldn't be able to see it. Look, we are not doing field theory here. We have fixed Hilbert spaces.
Because because you have to, I guess you need to put it additionally, because Hamiltonian alone, because you need the commutation relation or commutation, anti-commutation to be preserved in your transformation.
This is one of the questions I have. I don't know how to answer it yet. Maybe in time I will find my answers.
I'm a bit
but
confused
is it because Schrieffer-Wolff in this form, I'm showing you here, this works when your Hilbert space is fixed. Field theories don't work with fixed Hilbert spaces. You create particles at will, you destroy particles at will. This basically, you jump from one Hilbert space n particle to n-1, n+1 particle. Everything floats around. This whole formulation doesn't make any sense in this kind of language. So, what is the version of Schrieffer-Wolff transformation in field theory? Is it the Bogolyubov transformation? Is it something else? It's for sure, effective theory is like a bread and butter of condensed matter, of course. That's why I warned you that when my story was superconductivity, it's presented in field theoretical language. So it's not it didn't really, Schrieffer didn't use his transformation to actually, construct his Cooper pair PCS theory, but they were doing effective theories, and there were some, kind of transformations that reduce the bigger systems to smaller systems, but in field theoretical way, which is, something that we won't be touching, at least on this.
So even because you are doing perturbation and you are truncating at a certain order. So if you are doing a full unitary, maybe the appropriate algebra will be preserved, but since you are truncating, that's what my...
If you want to preserve something, you have to adjust what you are doing. You might require a little bit more from an S, your generator S, than just you might additional constraints that would put extra form, extra bits. Maybe if one preserves some commutator, I don't know. This is depending on your problem. So it's look, it's all extremely fascinating and deep, and simple formula don't be like some of my colleagues, older colleagues, who just look at it, this is just bullshit. Schrieffer, just a perturbation theorem. Just look. Probably if it has name attached to it, probably there's some story behind it. Don't be a bureaucrat, don't follow procedure. Think where the procedure comes from. Ask those questions. Dig in. That's probably more valuable than just following whatever you do with just following some procedure. If you just go deeper, you might learn some amazing stuff. And I'm tired. I'm spent. I was yapping. I was trying to convey this. Hopefully, I conveyed the amazingness and weirdness of this all. I'm afraid looking at the time. But let's. Okay, so that was a propaganda part. Next lecture is the last one this semester. We'll take a summer break, and the last one will be basically formalization of the whole, actually procedure. We will define procedure. Check the diagrams, do the radius of convergence, some proofs. Maybe I will talk about how they are attained. We'll see. We'll do something. There will be something interesting there.
Yes.
There isn't, but it's 3 hours.
Sorry, you shouldn't talk. I'm sorry.
Yeah.
Iran is
Okay.
not that cold country. They are not used